Good evening, everyone. This is Fluidization Engineering course live interaction session. Uh, so we'll start the session by 6:05 p.m. We'll wait for some more people to join the session. So it's time. We'll start the session. So this is the NPTEL course Fluidization Engineering. And the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. So I am the TA for this live session. I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So I am Anchor Kartika. So this session will happen every week, Friday from 6 p.m. to 8 p.m. throughout the duration of the course. So each week we'll be having one session where we discuss the problems similar to the that week's assignment problems, which would be helping you guys in solving that assignment problems. So apart from that, if few people have any questions uh, regarding the course, you people can always ask. So now we'll move on to session. So yeah, so those are following the course regularly from week 1 onwards would know that this is the course layout. So from in the week 1 to 2 we have seen the introduction to the fluidization and the advantages and disadvantages of the fluidized beds and various applications of the fluidized beds. So we have seen what is fluidization. Fluidization is nothing but where we pass the fluid inside the packed bed at a sufficiently high velocity so that the particle starts behaving like a fluid. Uh, the fluid-like behavior is imparted into the solids. This has various advantages like uniform heat and mass transfer would be taking place inside the fluidized beds. So it would enhance that, and also in the packed bed there are chances for hotspot formation, which is rectified over here. And the disadvantages are also there, like erosion happening because of the particles movement inside the bed. And also we saw the applications like in fluidized bed, it is used, fluidized beds are used in chemical industries for processes like fluid catalytic cracking and polymerization, like gasification, biomass gasification, and so on. So there are various applications in industries for the fluidized bed. So this is a very hot topic as a whole. In BTech we would have studied it as a small as a part of the course like fluid mechanics or so. So in here this course is completely dedicated to the fluidized beds. So what are all the associated things we would be learning in this course? So since week 1 to 2 was dealing with that, and week 3 we saw the characteristics of solids, classification of solids, how particles can be classified when it is in the fluidized bed. For example, we saw the GELDAT classification of solids where we divided it into 4 groups: GELDAT A, B, C and D, where C is the smallest and D is the largest, and also each has its own application. For example, GELDAT deep particles were used in spouted beds, and it is we also saw how it is very difficult to fluidize GELDAT C particles, while most fluidized beds use GELDAT A or GELDAT B particles. And also flow characteristics and its outline in different types of fluidization. And week 4 to 5 we would be seeing flow patterns of fluidization systems, flow pattern transition, flow pattern map, frictional pressure drop and its model to analyze, solid movement, mixing, segregation and staging. So there are various patterns like fluidization. We know fluidization as a single term, but in that fluidization there are various types like particulate fluidization, bubbling fluidization, slug fluidization, churn fluidization, pneumatic transport, everything. It depends on the fluid velocity, how fluid velocity is increasing and how much it is in excess of the requirement. So based on that, the fluidization can be classified into different groups. So all these things would be having different applications. So these are the contents for up till this week. In the coming up weeks, we would be dealing with gas distribution and special focus on bubbling fluidized beds, because we in some applications it is ideal to use bubbling fluidized beds. At the same time, we need to control the bubble formation. When we are dealing with gas solid fluidized beds, bubble formation poses some serious issues with mass transfer. So bubbling fluidized bed, entrainment and elutriation from the fluidized beds and attrition, mass transfer phenomena and heat transfer phenomena. All these things would be dealt in the following weeks. So for the books and references for the course, the first book is Cooney and Levenspiegel's Fluidization Engineering. It covers almost all the things that required for understanding fluidization, basics of fluidization. And next one is the Gidaspo's multiphase fluid flow and fluidization, continuum and kinetic theory description. So this one also we saw that this also covers fluidization, and special mention is given to the modeling part, uh, where we use the continuum and kinetic theory. For example, what is kinetic theory? In kinetic theory of gases, we deal with the flow of gases, right? Similar to that, we make assumption for the particles, where we assume the particles to be as a continuum. They are discrete entities. Each particles are discrete entities, whereas in the continuum theory and by using kinetic theory description similar to that for the gases, we call it kinetic theory of granular flow, KTGF. So by using that, we model the particles, that is solids, inside the fluidized bed as a continuum. So solid would be one continuum phase and the fluid would be another continuum phase. So that is one aspect of modeling the fluidized bed. So that is best described by Gidaspo, where he implemented that KTGF, that is kinetic theory of granular flow, similar to kinetic theory of gases. And the third one is Gibelaro's fluidization dynamics. And fourth is our professors S.K. Majumdar's hydrodynamics and transport processes of inverse bubbly flow. First edition. So these are the books and references for the course, and we'll start with the problems for this week's course. Like I am repeating all these things regarding the course layout and the books and references because few people might be new to each week. So to cover them and give them an idea, I am dealing with that. If not, you can skip the initial part and directly join this one. So in last week's class, we were dealing with the classification of solids and the different regimes of fluidization. Based on what aspect, in which regime of fluidization the particular phenomenon is taking place. So this week the main focus is on pressure drop inside the fluidized bed. So we'll just see the question 1. In question 1, it is given that with the increase of pressure at a constant mass flow rate, the overall volumetric mass transfer coefficient increases. Option B, it is decreases. Option C, it remains constant. Option D, none of the above. So what happens when there is increase of pressure at a constant mass flow rate? So we all know that the pressure variation inside the bed poses some it is a major factor that governs the fluidization, right? So what happens when we deal with the when pressure is increased? So when pressure is increased, the bubble size decreases. For example, we'll consider it as, here we are having the pressure. With increase in pressure, we have diameter of bubbles decreases. So what happens when bubble size decreases? We have increased mass transfer rate. That is the bubble, sorry, not increased, like there would be many number of bubbles. So many bubbles would be there, like bubbles would be broken down. So there would be n number of bubbles because of the decrease in the bubble size, and this would lead to, here we have fluid, right? The bubble to fluid mass transfer coefficient would be decreased. like the mass transfer coefficient would be decreased when the bubble size decreases. So because with increase in pressure, the diameter of the bubbles gets decreased, like a bubble diameter is decreased, and because of that the mass transfer coefficient, that is the mass transfer from the bubble to the fluid, would be reduced. So the mass transfer coefficient decreases. So answer to the first question is option B, decreases. Now we'll go on to question 2. In a fluidized bed, as the fluid's approach velocity is increased, the pressure drop is increased, decreased, remains constant, none of the above. So consider this, and delta P versus fluid velocity. Consider the packed bed. So when it is increased, like when the velocity is increased, the pressure drop keeps increasing. After which, once the bed is fluidized, the phenomenon or the pressure drop would remain constant. But with as the fluid's approach velocity is increased, the pressure drop is also increased. So the answer to question 2 is option A, that is increased. We'll just see question 3. In question 3, it is given that pressure drop in the riser of the fluidized bed may be developed on the basis of Bernoulli's equation, Newton's equation, Fick's equation, none of the above. So we all know that Bernoulli's equation is associated with the energy conservation inside the bed. So similar to that, the pressure drop in the riser of the bed is modeled based on the Bernoulli's equation only, like how head losses is happening inside the bed. Based on that, the pressure drop in the riser of the bed is developed. So answer to question 3 is option A, that is Bernoulli's equation. We'll go to question 4. In question 4, it is given that the pressure can change the bubble size in the bubbling fluidized bed. With increase in pressure, the bubble size increases, decreases, remains constant, none of the above. So in the previous thing itself we saw how with increase in pressure the bubble size becomes smaller. That is, the bubbles would be reduced in size. So the mass transfer coefficient would also be decreased. This one we saw in the first question as part of mass transfer coefficient. But in this question it is asked regarding the bubble size. So similar to that, with increase in pressure, the bubble size reduces or it decreases. That is, so question 4, the answer is option B, that is decreases. The pressure drop inside the bed may be due to option A, the friction and acceleration of solids and gas. Option B, it is friction head and acceleration of the solids and gas. Option C, it is friction and heads of the solids and gas. Option D, none of the above. So, how do we go with Bernoulli's equation, where there we assume that total energy is constant, right? Total energy is equal to so what would be the total energy comprised of? It would be potential energy, kinetic energy, and the energy due between solids and gas interaction, or solid and fluid interaction? Forgive my bad handwriting over here. It is very difficult to write it from laptop. So similar way we associate the delta pressure drop delta P as these three things only. The first one is okay. Question 5. So pressure drop inside the fluidized bed. It is dP by dZ. Let us keep it as pressure drop inside the fluidized bed. So, okay. The total dP by dZ inside the fluidized bed would be equal to dP by dZ because of the head loss, the total pressure drop inside the fluidized bed is equal to first one because of the head loss, and this one is corresponding to the potential energy of the gas and the solid phase. So the total pressure drop due to head plus total, next what comes we have seen is acceleration. Acceleration by dz. This one is due to friction. Friction would be happening between solids and fluid, and solids and the wall, and fluid and the wall, everything. So the pressure drop inside the fluidized bed is happening due to three factors. One is due to the head, next one is due to the acceleration, next one is the friction. So this one is similar to the potential energy term of gas and solid, and this is the other factors: acceleration between the of solids and gas, friction, everything. So all these factors only influence the pressure of inside the fluidized bed. So in the last question it was asked that question 5, the pressure drop inside the bed may be due to friction. It is true. Acceleration of the solids and gas, again this is true. Friction, head and acceleration of solids and gas, option B is true. Friction and heads of the solids and gas, option C is true, but it doesn't include acceleration. Similarly, option A is also right, but it doesn't include heads. So option D is none of the above. No, that is not the right answer. So the answer to the question 5 is option B, because the pressure drop inside the fluidized bed is due to head, acceleration and friction. Friction, head and acceleration of the solids and gas. So this is the answer to question 5. Now we have a problem in question 6. We will solve this. First, it is given that air, we all know air has the density of 1.22 kg per meter cube, dynamic viscosity 1.9 into 10 power minus 5 pascal second, is flowing in a fixed bed of diameter 0.5 meter and height 2.5 meter. The bed is packed with spherical particles of diameter 10 mm. Void fraction is 0.38. The air mass flow rate is 0.5 kg per second. Calculate the pressure drop across the bed of particles. Here the question is, we have a fluidized bed with air, I mean not fluidized bed, sorry, it is a fixed bed. We have air passing inside the bed. So the air density and viscosity is given, and the bed diameter and height of the bed is given. Height here denotes the particles packing height. And void fraction is given, and then what else is given? Air mass flow rate is given, and we are asked to calculate the pressure drop across the bed of particles. So we'll calculate it. Question 6 solution. What is the first step, guys? When we are dealing with any problem, we should write given. And here we'll write whatever it is given, and we'll analyze whatever is given. So first it is given density, dynamic viscosity, everything is given, flowing in a fixed bed. Bed dimension is given, diameter and height is given. So here also we can write air. So again fixed bed, diameter and height is given. The bed is packed with spherical particles, and regarding particles, spherical, it is given spherical particles of diameter 10 mm, and void fraction it is given as 0.38. Air mass flow rate is 0.5 kg per second. Mass flow rate is 0.5 kg per second. Calculate the pressure drop of across the bed of particles. To find pressure drop across, so this one is the given and this one is the to find. So from this we need to find the pressure drop across the bed. So what equation we all get to know from this? Question 6 solution. So in this we tend to use Ergun's equation. What is Ergun's equation? How will we use things? dp by, okay, else I can write it as insert equation del P by L is equal to 150 into V into mu 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 150 into 1 minus epsilon the whole square divided by 5 dp square into epsilon cube plus 1.75 equation. We need to insert rho v square 1 minus epsilon pi 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 dp epsilon. So this one is the Ergun's equation. We all know this. But in this we need to identify if it is a laminar flow condition or the turbulent condition, and then use it accordingly. So first we will calculate what was asked. Actually it was asked for pressure drop. So we will calculate a Reynolds number. EP, particles Reynolds number. So what is it? It is rho v dp by u. I hope you all know what all the variables are. Like v is the superficial gas velocity, mu is the fluid viscosity, epsilon is the white fraction, and dp is the diameter of the particle. Or else, if needed, we can write it over there in the given itself. For example, this one is air density rho, dynamic viscosity mu, and mass flow rate, fixed bed height, spherical particles of diameter. So here we will substitute everything. First it is 1.22 into, okay, we need to first calculate V. V is equal to here, okay, V is asked. So first we should find the velocity, inlet velocity. Here we have mass flow rate, that is m dot is given, right? Okay, we will put it as this. This one divided by rho, that is fluid density, would give us volumetric flow rate into so we need the volumetric flow rate meter cube per second, we will get divided by meter square, that is in area of the column. area of the column. That would be m dash by rho divided by pi into pi by 4 by r square, radius of column. Okay, sorry, by r square, right? Yeah, this one would be doing, and here it is given that diameter d column. From this we'll substitute everything first. 0.5 kg per second divided by 1.22 divided by pi 3.14 into r is 0.25 square, 0.25 square. Yeah, now we'll calculate this and we'll identify what value it is coming. 0.5 divided by 1.22. You people can also calculate this and let me know the answer. Into 0.25 square. 2.08 meter per second. So V is equal to 2.08 meter per second. Okay, now we should find the REP. That is REP is equal to rho. We have 1.22 into 2.08 into dP is 10 mm. So 10 into 10 mm is 10 into 10 power minus 3. So 10 power minus 2.01 divided by mu is 1.9 into 10 power minus 5. Minus 5. So this, what value is this giving? 1.22 into 2.08 into 0.01 into 10 power 5 divided by 1.9. It is giving us 1335.58. So this is, what does it mean? It is greater than 500. So this is turbulent regime. So it is sufficient if we use the second part of the equation alone. That is, in this we need not go for the first part. Up till this part is sufficient. That is equal to, yeah. So now we'll substitute everything over here and we'll find the value. So delta P is equal to 1.75 into, okay, here we have not given it as L. Height L is equal to 2.5. 1.75 into rho is 1.22 and it is 2.08 V square epsilon is 1 minus 0.38 divided by 5 is right, and it is 0.01 meter and 0.38. And on total we should multiply by 2.5, that is length of the bed. So come on, please calculate and let me know the answer. 1.75 into 1.22 into 2.08 into 0.62. Okay, divided by 0.01 into 2.5. We are getting 26091 Pascal. So delta P is equal to 26091 Pascal, or we can write it as 0.260. What was it given actually? 261 into 10 power 5. So answer is this one. So the answer to this question is option D, 0.264 into 10 power 5 Pascal. So this is how we calculate the pressure drop inside the bed. So if you people have any doubts in this problem, please let me know. Otherwise, we'll move on to next question. Very simpler problem. Here to find the pressure drop, we are initially using the Ergun's equation. In order to identify which part of the Ergun's equation to use, we identify whether it is inside the laminar regime or turbulent regime by calculating the Reynolds number. And from Reynolds number, we found out that this one is falling under the turbulent regime. So we are using the Burke-Plummer equation, that is the second part of the Ergun's equation, and we are finding out the pressure drop. So this is question 6. I hope this is clear. Now we'll go on to question 7. When fluid Reynolds number is less than 2300, the fluid friction factor FF is calculated using Blasius's formula as 16 by REF, 24 by REF, 36 by REF, 18 by REF. So we all know that when we are okay. If it is given, it would be easier for us. So we all know that if it is less than 2300, that is inside a fluid flow regime. How to calculate the fluid friction factor? When we are using Blasius's formula, so we know that we have studied it in fluid mechanics that this laminar regime we would be getting the fluid friction factor as 24 by REF. So answer to this problem is option B, that is 24 by REF. So we'll go to question 8. Question 8 is again a problem. In this question, it is asked that a 0.5 meter high bed made up of a 1 mm diameter glass spheres is to be fluidized by water. If at the point of incipient fluidization, the bed voidage is 40%, the pressure drop across the bed is dash. So, we'll go and solve this problem. This question 8. First, we'll write the given things. What is given in this problem? So we'll write 0.5 meter bed height. So bed height that is L is equal to 0.5 meter diameter of bed d bed is equal to okay. Okay, diameter of bed is not given, diameter of particles. So diameter of particles is given as 1 mm, that is 1 mm, and is to be fluidized by water. So the fluid is given as water. So we know the density of fluid. So we'll write rho wells insert is equal to 1000 kg per meter cube, and okay, density of particles is also given. And it is 2500 kg per meter cube, and is to be fluidized by water, and it is given incipient fluidization, that is at the minimum fluidization condition the bed voidage is 0.4, that is 40%. So what is the pressure drop across the bed? uh, Here it is given epsilon insert use mf is equal to 0.4. So to find what pressure drop, pressure drop. So from this question, these are the given, and we need to pressure drop. We need to find the pressure drop across the bed. Across bed. So how to find the pressure drop across the bed? At the minimum fluidization condition, we calculate the delta P by delta L as mm, mm, delta P by is equal to rho minus rho F into G into 1 minus epsilon. So in this we'll substitute the given all the given values, and we'll find out the delta P. So delta P is equal to, we know the diameter density of the particles is 2500 and density of water is 1000 into 9.81 into epsilon is 1.4. And what was the length of the bed? It is 0.5 into 0.5. So we'll calculate this and we'll find out. So 1500 into 9.81 into 0.6 into 0.5. We are getting 4414, that 4414.5 Pascal. And in the given question it was about in kilopascal, so it is 4.4 kilopascal. So sorry, the answer is option A, 4.4 kilopascal is the right answer. I hope the answer is clear. Now we'll move on to question 9. In question 9, there are two parts of the question. So we'll go step by step. In the first question, it is asked that a packed bed consisting of 1.96 kg of solids of density 2.8 gram per centimeter cube is contained in a cylindrical vessel of 10 centimeter internal diameter and the bed height is 20 centimeter. What is the volume of the vessel occupied by the bed in ml? 157, 1570, 3140 or 6280. So yeah, we'll calculate it. And yeah, first we'll calculate this. Okay, mass of solids. Mass of m is equal to 1.96 kg. Okay, we'll keep it as solids. Density, that is, insert symbol, row, close. Point 0.8 gram per centimeter is contained in a cylindrical vessel. Vessel diameter D is equal to 10 centimeter. Bed height is 20 centimeter, which bed is equal to 20 centimeter. Volume of the vessel is, okay, to find volume of the vessel occupied by bed in ml. First, we'll find out the volume of the bed. Okay, volume of bed. You know the, so it would be pi by 4 into d diameter of bed pi by 4 d square into h bed, that would be equal to 3.14 into, what is the diameter of the bed again? It was 10 centimeters, so 10 into 10 power minus 2, 0.1 I into 0.1 into 0.2 divided by 4. What is it coming? 3.14 into 0.1 into 0.1 into 0.2 divided by 4. It is 1.57 into 10 power minus 3 meter cube. Since it is asked in ml, how to convert 1 meter cube is equal to 1000 liters, and so it is 1.57 liters, or else how to put it in ml, 1570 ml. So answer to this is option B, that is 1570 ml. I hope this is clear. Now we'll go on to question 9b. This is a continuation to the previous question, in that it is asked that volume of the solids in the vessel. So previously what the question was, volume of the vessel occupied by the bed. So we calculated by using the volume of height of the bed, height of the particles in the bed, and calculated directly the volume of the bed. Now it is asked that volume of solids in the vessel. So similarly, all these is just given. And yeah, question 9b. Now it is as volume of solids inside the vessel. Solids in the bed or vessel, something in ml. So we'll go to how to do question 9b solutions. First we need to find the we have the mass of the solids and density of the solids. So again this is a straightforward question. Volume of solids is equal to mass of solids by density of solids. This would be giving 1.96 kg divided by 2800. I guess that was a 2.8 or 2800 kg per meter cube. What would this give? 1.96 divided by 2800. It is giving 7 into 10 power minus 4 meter cube. Again, it is 7.7 liter or 700 ml. I am typing out all these in the hope that it would be easy for you to follow the questions in a step-by-step approach. So only because of that I am typing it out. So please listen to the question and follow it and do it up in a paper, so it would be easier for you guys. And question 10 again is a follow-up question for the ninth question, or we can put it as 9C also. 9C, just to mention, it is a follow-up question. So what was asked here? Porosity of the bed. Porosity of the bed. Now it is a very straightforward approach. Uh, okay. So, how do we find the solid fraction inside the bed is equal to volume of solids divided by volume of bed. So what would this is from the previous two questions. We found it as 700 ml and 1570 ml. So volume of solids inside the bed was 700 ml and volume of the total packed bed was 1570 ml. So dividing both would give us the answer as 0.4459. So what would the void fraction or porosity value would be? 1 minus 0.4459. This would give us 0.5441. Yeah, so it is 0.5441 and in the question it was asked 0.554. Yeah, 0.5541. So answer to this is option A, 0.554. So this is the solution. This is how we approach the problem. So we'll just take a quick 5 minutes break before resuming the session. We'll meet sharp at 7:10. Okay, guys, we'll start the session. In question 11, it is asked that we'll go on to question 11. And in question 11, it is mentioned that the role of pressure drop in fluidization governs the pattern of energy dissipation, change the fractional holdup of the phase, changes the bubble size in bubbling fluidized bed, and all the above. So we know that the pressure drop in fluidization, it changes the bubble size, and also because of that fractional holdup of the different phases affects, and the energy dissipation also affects. So the answer to this question is all the above. Under higher superficial gas velocity, the frictional pressure losses with gel dot B particles are greater than those with gel dot A particles. Gel dot A particles are greater than those with gel dot B particles. Gel dot A particles are equal to that with gel dot group B particles, or none of the above. Usually what happens is that under some superficial gas velocity, keep it 7 or something, the frictional pressure drop doesn't change with particle diameter. But under higher superficial gas velocity, the frictional pressure losses for group A particles are greater than those with group B particles. That is, for smaller particles, it is greater than the larger particles. Keep in mind like that. Group A particles are greater than group B particles. That is option B. We'll go to question 13. In question 13, it is given that the pressure drop across the bed, that is delta P at the particulate regime, is equal to the effective weight of bed per unit area, greater than effective weight of bed per unit area, or smaller than the effective weight of the bed per unit area, or none of the above. We know the answer to this question as equal to the effective weight of bed per unit area. This we have seen in the introduction to the fluidization, where at particulate regime is the initial fluidization regime, that is after minimum fluidization velocity, where the bed expands equally. So at that point what happens is that the drag force experienced by the particles would be because of the particles would be equal to the gravitational pull acting on the particles. So that is, the pressure drop is equal to effective weight of the bed, that is together with the particle and the fluid per unit area. So it is equal, not greater or not smaller. So answer is option A. Another problem is here, another fluidized bed. Okay, here we'll keep it as a fluidized bed. A fluidized bed contains 1.8 kg of solids of density 1.3 gram per centimeter cube in a cylindrical 30 centimeter internal diameter vessel with a bed height of 20 centimeter. The bed porosity is what? So this question is kind of a combination of all the three questions that we saw before. A fluidized bed contains 1.8 kg of solids of density in a cylindrical diameter. So how to calculate porosity? So we'll just take out question 9a, 9b and 10, and together we'll solve that, or else we'll go by this only. What is question 14a, solutions? First we'll write given. Solids. Okay, solids mass is 1.8 kg and density is 1.3 gram per centimeter cube. Vessel diameter uh, is equal to 30 centimeter, bed height is 20 centimeter. H bed. And find porosity. How do we calculate porosity? Volume of solids by volume of, this gives solids fraction, and 1 minus this gives porosity. So first we should find the volume of solids is equal to mass of solids by density of, what does it give? Mass of solids was 1.8 kg, and this is 1300, 1.8, and this is 1300 kg per meter cube. That was given in gram per centimeter cube. 1.8 divided by 1300 gives 1.38 into 10 power minus 3. Volume of bed. This is a cylindrical column, so it is 3.14 into 30 centimeter. So it is 0.15 radius into 20 centimeter, that is 0.2. What does it give? 3.14 into 0.15 square into 0.2, 0.01413 meter cube. So porosity value would be 1 minus 0.00138 divided by 0.01413. 0.00138 divided by 0.0401413. 1 minus this would be 0.9023. So the porosity is given as 0.9023. We will check the options. It is given option D, that is 0.902 is the right answer. So that is option D. So this one is similar to that ninth question we saw. Together in a single question, it is asked to calculate the porosity. So we calculated it by calculating the volume of solids inside the bed and the volume of the bed, and that fraction, that is the volume of solids by the volume of bed, gives the solid fraction inside the bed, and 1 minus solids fraction gives the void fraction or the porosity of the bed. I hope this is clear. If you have any doubt in this question, please ask, or else we'll move to question 14b. Okay, in question 14b, it is asked that the particles used above have a diameter of 200 micrometer, and the fluid density and viscosity are 1.29 kg per meter cube and 2 into 10 power minus 5 pascal second respectively. Terminal settling velocity of a particle is 0.783 meter per second. Particle Reynolds number is. So we need to find the particle Reynolds number from this. In the one of the previous One of the questions that we saw before was we found the particle Reynolds number, but in that case we found it to identify the flow regime. But in this it is a simple question. Directly it is asking to calculate the particle Reynolds number. So we'll write the given particles diameter diameter is equal to 200 micrometer. dp is equal to 200 micrometer. Fluid density is 1.929 kg per meter cube, and fluid viscosity 210 power minus 5 pascal second. Velocity is this, and particles Reynolds number we should find. So REP is equal to rho VDP So on substituting all these values, we would be getting 200 10 power minus 6 rho 0.783 V into dP. Rho is 1.29 divided by 2 10 power minus 5. What would the answer be? Okay, 20 into 0.783 into 1.29 divided by 2. 10.1007. So answer is 10.1007, that is 10.1. Answer is option B. I hope this is clear. Question 14B. So now we'll move on to question 15. If you have any doubt, please ask, or else we'll move on to question 15. I think that all the questions that are coming up below are theoretical questions. The accelerative pressure drop is the pressure drop due to the acceleration of particles from the inlet of the riser to the point where the particles attain minimum velocity in the riser, maximum velocity in the riser, velocity equal to the inlet velocity in the riser, none of the above. So the riser is there. What is the acceleration pressure drop denote over that? Acceleration pressure drop, in the pressure drop we have seen that it is due to friction acceleration between the solids and gas and the head. So acceleration pressure drop is the pressure drop due to the acceleration of particles from the inlet to the point where the maximum velocity is attained by the particles. Only then we get the acceleration pressure drop. So the answer to this is option B, that is maximum velocity in the riser. So between those 2 points only we calculate the accelerative pressure drop. Now we'll go to question 16. The total friction pressure drop is generated due to frictional force between gas and solid, frictional force between solid and walls of the bed, frictional force between gas and wall of the riser, and option D, all the above. So when we are dealing with the frictional pressure drop, it is due to all the factors contributing, like between fluid and the solid, or in our case it is gas and the solid, and also that is particle and the fluid, and between the particle and the wall, that is solid and the wall, and between the gas and the wall, whatever the frictional force between acting between these three factors, like fluid, or the fluid wall, or the particle wall, or the particle also. So all these three comes under the contribute to the total frictional pressure drop. So answer is option D, that is all the above. That is frictional force between gas and solid, frictional force between the solid and the walls of the bed, and frictional force between the gas and the walls of the riser. Now we'll go to question 17. In question 17, it is given that frictional force per unit volume between the solid phase and the wall can be calculated by Bernoulli's equation, Fanning's equation, Dalton's equation, none of the above. Bernoulli's equation we used to calculate the total pressure drop inside the fluidized bed or inside any system for that matter, and friction factor is calculated by using fanning. I hope you all remember FF, that is fanning friction factor. The friction factor, that is FF, it is calculated by using the Fanning's equation. So answer to question 17 is option B, that is Fanning's equation. We'll go to question 18. Due to the lesser concentration of the solids in the riser, the friction between gas and solids may be negligible. Solids in the walls of the bed may be negligible. Gas in the wall of the riser may be negligible. All the above. When there is a lesser concentration of solids inside the riser, what can be neglected? When the solids are less, we can see that solids in the wall concentration, it plays a major role, because even though it is less, it still plays a role. But in case of gas and wall, since gas concentration is not significantly affected, the gas in the wall of the riser would be still playing a role. So gas and solids, on the other hand, if there is a lesser concentration of solids, imagine the thing that gas would be freer to move. That is, the gas movement would not be affected by the solids movement. So the friction between the gas and the solids can be neglected, because gas movement would be taking place on its own, in which case the solid concentration is very less, so it would not be hindering the movement of the gas. So gas and solids may be negligible. So the answer to this question, that is question 18, is option A, gas and the solids may be negligible. We'll go to question 19. With increase of solids concentration, even if the operating conditions have almost the same solids velocity, the frictional pressure losses decreases. Option B, increases. Option C, remains the same. Option D, none of the above. Think in this case where solid concentration increases, all other operating conditions like solid's velocity remains the same. What would be the case of frictional pressure loss for the case with lower solid concentration and higher solid concentration. Here we all know that with lower solid concentration, we can neglect the effect of frictional force between the gas and the solids. But with increase in the solid concentration, they play a major role, thereby they have a very significant value. So obviously their value is increased. In that context, the frictional pressure losses again increases. So with increase of solid concentration, even if the operating conditions are almost the same solids velocity, frictional pressure losses increases. That is because of the interaction between the solids and the gas uh, are increased. The frictional pressure losses on the other hand also increases. So answer to this question, that is question 19, is option B. We'll go to question 20. Question 20. Frictional pressure loss increases with increase of solids velocity and gas superficial velocity. Option B, increase of solids velocity and decrease of gas superficial velocity. Option C, decrease of solids velocity and increase of gas superficial velocity. None of the above. So, frictional pressure loss on the how it affects is that when solid velocity and solid friction solid sorry gas superficial velocity, both of them increases, the interaction between the solids and the gas would be much more. So in that case, the frictional pressure loss would be more. On the other hand, if either one of them is very low, what would happen is that the frictional pressure loss would be very low compared to the case where both of them were higher. The interaction between them would be very low, like so the frictional pressure loss in turn would be very low. So that in this case, what happens is that frictional pressure loss increases when both the solids velocity and the gas superficial velocity increases. So answer to this question is option A, that is increase of solids velocity and gas superficial velocity. Frictional pressure loss increases with increase of both. I hope this is clear. If you have any doubt, please let me know. I'll try to explain it in a more clearer way. So we'll go to next question. Yeah, these are all the 20 questions for today. If you people have any doubts, please feel free to ask now. We'll solve all your doubts, and even if you have any doubts from the previous weeks, you can ask. We'll have five. We'll wait for 5 more minutes for the doubt clearing. But the question for today is done. If you don't have any doubts, you can leave, or you can wait and participate in the discussion. Yeah. So I guess no one is having questions. So we'll just have a quick recap of today's session and we'll close today's session. So yeah, in today's class, it was more about pressure drop, frictional pressure drop between the particles, and in today's class, we saw the total pressure drop inside the fluidized bed is a factor of contribution from the pressure drop due to head, pressure drop due to the acceleration between the solids and the gas, and the frictional pressure drop. So we saw how the increase of pressure drop affects the bubble size. The bubble size gets decreased and the mass transfer also, mass transfer coefficient is also decreased in at with increase of pressure. So this one is fluid's approach velocity is increased at the particulate regime. Before the particulate regime, we know that with increase in the particle velocity, fluid velocity, the pressure of inside the bed increases, but once after fluidization, they remain constant. The pressure drop in the riser may be calculated by using Bernoulli's equation, and bubble size decreases with increase in pressure drop, and pressure drop may be due to friction and head and acceleration of the solids and the gas. So we saw a problem how to calculate the pressure drop by using Ergun's equation. In this we found this is Ergun's equation, this is the Kozny-Kármán equation, and this is the Burke-Plummer equation. So together when put it inside is known as Ergun's equation. So this is for the laminar regime, this is for the turbulent regime. So initially we calculate the particle Reynolds number, and since it was greater than 500, we know it is in turbulent regime. So we use the second half of the equation and calculate the pressure drop. We get this as the answer, and this is for calculating friction factor. Fluid friction factor, we use Blasius formula, and for laminar regime that is less than 2300, we go for 24 by REF. And in question 8, it is about the calculation of pressure drop at the incipient fluidization or the minimum fluidization condition. We use this formula ρP minus ρf into G into 1 minus epsilon. That is, we calculate that the pressure drop is equal to the weight of the particles inside the particles and the fluid inside the bed. That point it becomes equal, right? It is balanced by the weight. So in that aspect we get this formula and we use it for the calculation. And question 9, it was about packed bed containing a solids, and we are 9A, 9B, 9C or 10 were all as part of a similar question or part of a single question, where first we calculate the volume of the vessel occupied by the bed. Volume of the vessel occupied by the bed, and next is the volume of the bed alone, that is the solids alone. So this one is a direct question. Here we use the volume of cylinder formula, and here we use the mass by density formula. And from this, porosity is calculated by first obtaining the solids fraction, which is nothing but the volume of the particles by the volume of the bed, that is the vessel occupied by the bed. So that gives the solids fraction. 1 minus the solids fraction gives the porosity value. So the role of pressure drop in fluidization is affecting almost everything like bubble size, fractional holdup, and the pattern of energy dissipation. And we know that at lower superficial gas velocity, the frictional pressure drop doesn't affect change with the particle diameter. Whereas with higher superficial gas velocity, frictional pressure loss of gel dot A particles, that is the smaller particles, are greater than those with the gel dot B particles. Pressure drop across the bed at particulate regime is equal to the effective weight of the bed per unit area. And this was again a similar question to the one we saw in question 9, where we calculate the porosity of the bed. And this is calculation of the Reynolds number. We know that how to calculate Reynolds number. And accelerative pressure drop is the pressure drop due to acceleration of particles from the inlet to the point where the velocity is maximum velocity in the riser. And this is total frictional pressure drop is generated due to frictional force between the gas and the solid and the wall and the gas and the wall, all of the above. And frictional force is calculated using Fanning's equation. and lesser concentration, the friction between gas and the solids can be neglected. And with increase in the solids concentration, we need to include the friction force between the gas and the solids. Thereby, the frictional pressure loss increases. And frictional pressure loss increase with increase of solids velocity and gas velocity. Thereby, the interaction between them would also be increased. So, the pressure loss would also be increased. So, answer to this is increase of solids velocity and gas superficial velocity. So that's all for today's session. Thank you for attending today's session. I think there is a small correction. So yeah, I thank everyone for attending today's session. That's all for this week's session. We'll again see the problems and solve the next week's problem in next week Friday, same timing from 6 p.m. to 8 p.m. This lecture would be is available in the YouTube. So the links will be shared by the PMRF. Sorry, links will be shared by the NPTEL. So from there you can get access to these videos, and if you have any doubts or queries, please feel free to drop as comments in those questions. I'll be happy to answer those. And if other than that, if you have any doubts now, you can always ask. Yeah, that's it for this week. I thank you for attending. We'll meet again next week. Thank you. We'll close the session if you people have no doubts. Yeah, thank you.